we continue the discussion on the all integer primal algorithm with this example which we have been working out. Two variable problem with both constraints less than or equal to type, maximization with non-negative coefficients. We added slack variables x3 and x4 and started with x3 and x4 as the basic variables, and we introduced many primal cuts, and at some point we had reached this iteration where the present solution is represented by x1 equal to 1, z equal to 1. Now, when we look at this iteration, we realize that here the dual is infeasible, indicated by a negative sign. So, we enter this, and then we have to find out the row from which the cut will be generated. In this entering column, there is only one element with a positive sign, rest of them are all negative. Therefore, this is the only row with which we can make a primal cut. So, this will become a temporary pivot. Dividing by 18 and introducing an S6, we would have 19 by 18 with a lower integer value of 1, minus 21 by 18 will have a lower integer value of minus 2, and 18 by 18 will give 1. So, this will be the pivot element and this is the leaving variable. Now, we go back and continue the next table. We have a minus S5 and a minus S4 with x0, x3, x4, x1, x2, S1, S2, S3. S4 has entered, so we will have an S4 and an S6 leaves. So, S6 will be here. The pivot element will remain as a pivot element with a 1. Rest of the elements in the pivot row are divided by the pivot. So, you get 1 and a minus 2. As far as this column is concerned, it is divided by the negative of the pivot. So, you get a 3, 3, minus 18, 1, 2, 1, 2 and 3. This will become 1 minus 3 into 1, which is 4, 0 plus 3, 3, 19 minus 18, 1, 1 plus 1, 2, 0 plus 2, 2, 0 plus 1, 1, 0 plus 2, 2, 0 plus 3, 3. In fact, right here we can stop, the reason being we need to still evaluate this, we need to evaluate here. So, this will become 5 minus 3 into minus 2 is 5 minus 6, which is a minus 1, I get a minus 1 here. So, 1 plus 6 is 7, minus 21 plus 36 is 15, 2 minus 2 is 0, 3 plus 4 is 7, 1 plus 2, 1 minus 2 is minus 1, 1 minus 4 is minus 3, 1 minus 6 is minus 5. Sir, 1 minus 6 is minus 5 and so on, right. X2 is 3 minus 4 is minus 1 and so on. Now, we still have not reached the optimal because we find that this can enter. So, this enters, and then we find that this is the only one that can be a candidate. So, this will be a temporary pivot, this element will be a temporary pivot. So, we will introduce an S7 here, and there will be a 0, there is a 1 and there is a minus 2 that comes in. Now, this is the actual entering variable and this will be the leaving variable with this as the actual pivot. So, we do one more iteration here and we get minus S7 minus S6 x0 x3 x4 x1 x2 S1 S2 S3 S4 and S5. Pivot element remains as a pivot element, rest of them are divided by the pivot. So, we get 0 and a minus 2 here. This is divided by negative of the pivot. So, 1 5 minus 15 0 1 1 3 5 and 2. Now, because of the 0, the same column will repeat here to get 4 3 1 2 2 1 2 3 1, and this will become 3 minus 1 into minus 2, correct. 3 minus 1 into minus 2 is plus 1, and therefore, we can stop here because you have got the primal is feasible, dual is also feasible. For the sake of completion, we would do 3 minus 3 minus 10 is minus 7, minus 18 plus 30 is 12, 1 2 minus 2 is 0, 1 minus 2 is minus 1, 2 minus 6 is minus 4, 3 minus 10 is minus 7, and 1 minus 4 is minus 3. Therefore, this is optimal, both primal and dual are feasible. So, solution is x1 equal to 2, x2 equal to 2 and z equal to 4, we are trying to maximize x1 plus x2. So, this is how the all integer primal algorithm works. Now, the couple of issues, on one hand it is a very easy algorithm to implement, primal cut is also very easy to understand. The biggest hurdle in this algorithm is that we can very quickly get into degeneracy, which we have seen. For example, we have had some 4 iterations where the objective function did not move from 1, and after 4th or 5th iteration it came to, from here it moved to 4, but then again there is a degeneracy coming in. Every time a primal cut results in a 0 here, it will be degenerate, and this will very quickly get into a degeneracy situation, and you will realize that you are making too many unnecessary iterations before it converges to the optimum. This is the biggest drawback as far as this algorithm is concerned. So, you will end up having more iterations to perform. Nevertheless, if we want to work with an all integer algorithm or an all integer cut, this algorithm is easy. Generating the all integer cut is also not very difficult. It is very intuitive and it is not very difficult. So, this is how the all integer algorithm works. The last part of the module on integer programming is to understand the all integer dual algorithm, which again we will explain using an example. So, we have an all integer dual algorithm, and we explain it with a minimization problem. So, we minimize (8x1 plus 4x2 plus 6x3) subject to 4x1 plus 5x2 plus 6x3 greater than or equal to 18, 2x1 plus 3x2 plus 5x3 greater than or equal to 15, 4x1 plus 6x2 plus 3x3 greater than or equal to 20, xj greater than or equal to 0 and integer. Now this is exactly the opposite problem. It is a minimization problem with all constraints greater than or equal to type. So typically if it were a linear programming problem, we would have used a dual simplex to begin with. So we develop what is called an all integer dual algorithm, which has more or less the same properties as dual simplex. It will start with a primal infeasible and dual feasible solution and proceed till you reach the optimum. So we first create the table for this. We would start with x4, x5 and x6 as basic variables. So we will have an x0 here, x4, x5, x6 as basic variables. Now this is, remember we would have minus x1 here, minus x2 and minus x3. So when we write this as a maximization problem, you will have maximize minus 8x1 minus 4x2 minus 6x3 would give us 8, 4 and 6 here. And remember it is a dual algorithm, so dual will be feasible, which is what you have got here. Now this will become minus 18, minus 4, minus 5, minus 6, minus 15, minus 2, minus 3, minus 5 and minus 20, minus 4, minus 6 and minus 3. So when we write this in the standard form, this is what we get for the given problem. The given problem is a minimization problem with all constraints greater than or equal to type, and the right hand side values are non-negative. So this is what we have here. Now this will be at 0. Now the dual is feasible and the primal is infeasible. So we have to generate a cut by based on a dual simplex mode. So we take that row which has the most negative element here as the row from which we generate the cut. So you can either put an arrow here or just put a dash indicating that this row is the row from which the cut is going to be generated. The dual cut is slightly different from the primal cut. The all integer dual algorithm will have a pivot of minus 1. We have already seen that all integer algorithms will maintain the integer property by having a pivot as either plus 1 or a minus 1. Otherwise, when you divide it with other numbers, you will get fractions. So initial table will be integer. In the all integer primal algorithm, the pivot element will be a plus 1, and in an all integer dual algorithm, pivot will be a minus 1. Pivot will be a minus 1 because in the next iteration you will divide, here you will divide by the pivot, so some negative will become positive here, and when you divide it by the negative of the pivot, the positive here will be retained. So we need to maintain the feasibility of the dual, at the same time make one negative element positive in the next iteration. So what we do here is, the moment we decide this is the row based on which we are going to have a cut, we look at all the negative elements in this row. In a subsequent iteration you may have 0 or non-negative elements also, but we look at only the negative elements in this row, and you have a 4, 6 and 3 with negative values coming in here. Now for all these negative values here, whatever be the negative value, go back and look at these. Now we will look at all these 3, 8, 4 and 6, because the corresponding elements are all negative. Now among these the smallest is 4. Now what you have to do is, remember these will all be always positive, right, or non-negative. Now the smallest is 4, divide every one of these elements by the smallest to get, for example, 2, 1 and 1 lower integer values. So 8 by 4 has a lower integer value of 2, 4 by 4 will have a lower integer value of 1, 6 by 4 will also have a lower integer value of 1. Now what you have to do is, this becomes 2 by 4, which is half, 1 by 6, leave out the negative sign, 1 by 6 and 1 by 3. I repeat, having got this 2 1 1, now go back, leave out the negatives, take only those elements that have negative sign here and do this part. So 2 by 4 is half, 1 by 6 and 1 by 3, the smallest is 1 by 6. So if you take the smallest 1 by 6, now create a cut by multiplying this entire thing by the smallest number that you get, which is 1 by 6. In the subsequent iterations you will also understand it better. Now minus 20 divided by 1 by 6, this will be an S1 that comes in, minus 20 divided by 1 by 6 will be minus 4, minus 3 point something, which will give you a minus 4. Minus 4 into 1 by 6 is minus 1, lower integer value again, this is a minus 1, this will be minus 1 again. So, you will have all minus 1s coming in. Now, in this process we will ensure that, remember this 2 1 1 was written based on the minimum here, and in this process we will ensure that the pivot element is minus 1 corresponding to the minimum, and it is that minimum that will be the entering one, and this is the actual pivot that we have. Now continuing the iterations, we will have here minus x1 minus s1 minus x3, you have an x0 here, you have an x4, x5, x6 and x2. Pivot element becomes 1 by pivot, so it becomes minus 1 again. Rest of the elements in the pivot row are divided by the pivot to get plus 4, plus 1, plus 1. Here divide by the negative of the pivot, so basically you retain the same numbers, 4, minus 5, minus 3 and minus 6. Now what we have done in the process is that this minus 4 has become plus because the pivot is minus 1, and you will see later that the dual feasibility is maintained the way we carried out. The way we got these numbers, the numbers 1 by 2, 1 by 6 and 1 by 3, dual feasibility will be maintained, which we will see now. Now this will become 0 minus 4 into 0, correct, 0 minus 4 into minus 4, which will be, making a mistake, no, 0 minus this, in 4 into 4 will give you minus 16, minus 18 plus 20 is 2, minus 15 plus 12 is minus 3, minus 20 plus 24 is 4. If you go back and check x1 equal to 2 or x2 equal to 4 would give us z equal to 16. So, we are doing all right. Now, this one will be 8 minus 4 into 1, 4, minus 4 plus 5 is 1, minus 2 plus 3 is 1, minus 4 plus 6 is 2. The dual feasibility is maintained. Similarly, 6 minus 4 is 2, minus 6 plus 5 is minus 1, minus 5 plus 3 is minus 2, minus 3 plus 6 is minus plus 3. Okay. Now this is still primarily infeasible because of this minus 3. So this is the only row which has a negative, and this is the only one which we will use to generate a cut. In this case we had 3 negatives, we used the maximum, or the maximum negative element was used as the row from which the cut was written. Here there is only one element, so we will use this row and generate a cut. Now this has only two negatives, which are -3 and -2. Corresponding elements are 4 and 2 here. Divide by the smallest to get 2 and 1. Now this becomes 2 by 3 and this becomes 1 by 2. The 1 by 2 is smaller, so 1 by 2 will be the one which we will use. Now multiply to get create an S2. -3 by 2 is -2. 1 divided or 1 into 1 by 2 is 1 by 2, which will become 0. -3 by 2 will become -2. -2 by 2 will become -1. I repeat again, this is the row with which we would generate a cut. There are two negatives, -3 and -2. Corresponding to them you have 4 and 2 here, which I have written down here. Smaller one is 2, so divide these by the smaller to get 2 and 1. Now go back to the corresponding negatives, you get 2 by 3 and 1 by 2. 1 by 2 is the smaller one, so multiply with 1 by 2. -3 into 1 by 2 is -3 by 2, lower integer value is -2. 1 into 1 by 2 is half, which will have a lower integer value of 0. -3 into 1 by 2 is -3 by 2, which becomes -2, and -2 into 1 by 2 will give us a -1. Now pivot is -1, smallest will enter, pivot is -1. So now this x3 will enter and S2 will leave. So we will have another row that is created, x6, x2 and S and x3. I will have -x1, -s1 and -s2. Pivot element will remain as pivot element, -1, right. Pivot always becomes 1 by pivot, so -1 becomes -1. This is divided by the pivot, so I get 2, 0 and 2. This is divided by the negative of the pivot, so the same numbers come in, 2, -1, -2, +3, +1. Now this becomes -16 minus 2 into 2 minus 4 is -20. 2 plus 2, 4, -3 plus 4, 1, 4 minus 6 -2, 4 minus 2 plus 2. Repeat, -16 minus 2 into 2 -20, 2 minus 1 into 2, 2 plus 2 is 4, -3 plus 4 is 1, 4 minus 6 is -2, 4 minus 2 is 2. Now because of the 0, the same column will repeat, 4, 1, 1, 2, 1. Now this one will be 4 minus 2 into 2, 0, -5 plus 2, -3, -3 plus 4, 1, -6, -6, -12, -1, -2 is -3. This is what we get here. We have still not reached the optimum because we have a negative element here. So this is the one that will, there is only one negative, therefore this is the row from which we will generate the all integer dual cut. This has only one element, this has only one element, which is a minus 12. So, corresponding to that is actually 0. So, what we have to do is, remember this, now there is only one element corresponding to that is 0. The other thing that we need to do is, when we were here, we said for example, when we tried to generate the dual cut from this, we said there are two negatives, the corresponding were 4 and 2, and we divided with the smaller one, so that we get a 1. If the smaller one turns out to be 0, then you do not divide it by 0, instead you keep it as 1 always. So that what we will effectively have in this case is, the fraction that we will have here will be 1 by 12, and when we multiply we will get a minus 1 that is coming in here. That is what will happen in this case. So, when the smaller one becomes 0, you actually do not have anything. Whenever you have a situation where the smaller one or the smallest one happens to be a 0, that will become 1, and that will be the basis on which we will generate the cut. So, what we will have here is a 1 by 12 that comes in. So, we will have an S3 which is actually coming in. So, 1 by 12, so minus 2 into 1 by 12 have a lower integer value of minus 1, 2 and 1 by 12 will give us a 0, 12 and will give a minus 1, 3 by 12 will also be 0. Okay, just check this, the 0 is all right when we did that, right. I have 4 minus 2 into 2, what do you get here? 0 is okay. This was the pivot in the earlier iteration, we had this was the pivot. So, 4 minus, was this all right? Okay. So, we get 1 by 12 and we proceed here to get this, then we continue. We get a minus x1. So, this will be the entering, this will be the pivot finally, this leaves, so I get 20, 20. We have x0, x4, x5, x6, x2, x3 and S1 enters. So, I have S3 and S2. Pivot becomes 1 by pivot. So, I have a minus 1 here, dividing by minus 1 I get 1, 0 and 0. Divide by negative of the pivot, I will get a 0 here, minus 3, 1, minus 12, minus 3, 2. Now, I write this 20 minus 0 into 1 is 20, 4 plus 3 7, 1 minus 1 0, yeah, minus 20, minus 2 minus 2, minus 2 plus 12 is 10, 2 plus 3 is 5, 2 minus 2 is 0. Right. So, we can stop right here and say that we have reached the optimum. The reason being we are performing a dual simplex iteration, therefore this will not violate the dual feasibility condition. Nevertheless, we go back and check that we have the same thing repeating. So this, because of the 0 and the 0, the same two columns will repeat. So you will have a 4 1 1 2 1 0 and a 2 minus 1 minus 2 3 1 minus 1 that comes in. Now we have reached the optimum here. Now this is how the all integer dual algorithm works. I will rub this. This is how the all integer dual algorithm works. Now the all integer dual algorithm has the same advantages and disadvantages as the all integer primal algorithm. In a way, the dual cut is a little more involved than a primal cut. In the dual cut, we have to ensure that the pivot element is minus 1. So we need to go back and do a couple of additional computation before we generate the dual cut. Primal cut was a little more obvious than the dual cut. But all these things that we did, we need to remember again that this particular thing, that when the smallest element happens to be 0, we will have to keep it as 1 and it will automatically qualify to make the cut. When the smallest element is a non-zero element, then you divide so that you get a 1 and then you proceed. And in every stage you will only have to take the negative element and then generate the cut. The fraction that is obtained here is based on the negative elements that are there, and very intuitively you will understand that the whole thing is centered around ensuring that the smallest among the negatives is the entering column, the pivot turns out to be minus 1 and the dual feasibility is maintained. So all these three things are done by the set of rules that we have used. We have not proved those rules, but those will be the guiding rules based on which we will generate a dual cut. And in the next iteration we will realize that at least one negative element, because you are dividing with a minus 1, at least one negative element will become non-negative or positive. The dual feasibility will be maintained and there will be an increase or reduction in this case of the objective function. The all integer dual algorithm also suffers from the same problems of degeneracy that the all integer primal algorithm suffers. For example, we did have a degenerate iteration that comes in when this entering one has a 0, then you get into a degenerate situation. The value of the objective function has not changed, but this is non-optimal or infeasible to the primal, this is feasible to the primal. So this is another example of degeneracy, but degeneracy in a dual simplex iteration, degeneracy in a dual simplex algorithm. The primal degeneracy is slightly different from here. So you have to remember that it is again a case of degeneracy. Degeneracy can happen. With some amount of experience, or if you work out more problems, you will realize that the all integer primal algorithm is more prone to degenerate iterations than the all integer dual algorithm as a very general rule. However, the moment you get an entering column with a 0, automatically you will get a degenerate iteration. So both these primal and dual algorithms have difficulties of quickly getting into degenerate solutions. Other than that, they provide a means by which you have all integer algorithms, so you do not get into any fractions at any point in time. You carefully prepare or make the cuts such that the pivot element is a +1 for the primal algorithm and a pivot element is a -1 for a dual algorithm. Now the all integer dual algorithm is ideally suited for a problem which has a minimization, which has all greater than or equal to constraints, of course non-negative right hand sides and non-negative minimization problem with non-negative coefficients in the objective function. Whereas an all integer primal algorithm is suited to solve the dual of this problem, which is a maximization problem, with all constraints less than or equal to and a non-negative right hand side and all objective function coefficients non-negative. Now what will happen if we have a mixed problem? Say we either have a maximization or a minimization, some of them turn out to be negative here, some of them turn out to be greater than equal to, some of them turn out to be less than equal to. Can we do or have an all integer algorithm which can handle that? We will just take an example, we will not go through the entire solution, we will just take an example and see how it looks like and then leave it at some point to solve. So, we will take an example here. Suppose we have minimize 2x1 plus 3x2 plus 4x3 x1 plus x2 plus x3 less than or equal to 9, 2x1 plus x2 plus 3x3 greater than or equal to 7, 4x1 plus 6x2 plus 5x3 greater than or equal to 16, xj greater than or equal to 0, an integer. Suppose we take a problem like this, we will define an x4, x5 and x6 which will act as basic variables. So, you will have an x4, x5 and x6. It is a minimization. So, you will straight away have x1, x2, x3 written here and you will have 2, 3 and 4 and a 0. Minimization implies dual feasible. You may have a negative also here, then this will become a minus 3. Now, this will become, it is a less than or equal to constraint. So, 9, 1, 1, 1, this is a greater than or equal to constraint, minus 7, minus 2, minus 1, minus 3, so it will become minus 16, minus 4, minus 6, minus 5. Now, you can straight away proceed with an all integer dual algorithm. There are two negatives, take the most negative and proceed. So, this would give us all three are negative here. So, 2, 3 and 4. So, this will become 1, 1 and 2. So, it will become 1 by 4, 1 by 6, 2 by 5, 1 by 6 will be the minimum and you can generate an all integer dual cut and you can proceed. If you get into a situation where some of these are negative, then you will have to redefine the whole thing carefully by checking out, for example, this being the smallest. Among these things you will take only those which have positive and then you will proceed. So, you have to modify that rule suitably. It depends on whether you want to generate a dual cut or a primal cut. In this case, a primal cut is not possible. Primal cut would mean that you take an element whose dual is infeasible, only the negatives will enter. A primal cut will first have an entering variable and then a leaving variable. A dual cut will first have a leaving variable and then an entering variable. So, in this case a primal cut is not possible because the dual is already feasible. So, in this case only a dual cut is possible. If you had a minus 3 here, then a primal cut would have been possible. If you had a minus 3 here, then you can go back and do a primal cut with this entering, there is only one candidate. So, this will be the pivot and you will proceed. You can do that. You can also have a dual cut with this as the candidate, all three negative, but you will take only these two, 2 by 4, 2 by 5, 2 by 5 being smaller, you will generate a dual cut and you can proceed. So, very similar to a linear programming problem with mixed type, you could have a situation where both primal and dual could be infeasible and so on. Very similar to that situation, you may start with a primal cut or you may start with a dual cut. If the problem has an optimum, then you will realize that at least one of the cuts will be possible. If both cuts are possible, as in this example with a minus, then you could choose any one of them and proceed. But if you have a situation here where a primal cut is not possible and only a dual cut is possible, you will have to proceed with a dual cut. If the problem has an optimum, then it will somehow take you to the optimum through a series of primal and dual cuts. As I said, where both are possible, you can choose any one of them and proceed. The only thing that is not guaranteed is the number of iterations. It will eventually converge, but it might take longer or more number of iterations depending on the problem situation.
The IP, if the constraints form a feasible region that has no feasible integer solutions, but only a feasible LP, non-integer solution, then how will you know?
No, the integer will at some point show infeasibility to the corresponding. After all, in every stage you are only solving a linear programming, you are doing a simplex iteration. Therefore, as you add these cuts, you will finally get into a situation where you do not seem to have a feasible point to the LP. Maybe a cut would make the whole thing infeasible, and at that point infeasibility will be shown. Now again, infeasibility will be shown depending on what kind of a problem you are in. If you go back to infeasibility criterion of linear programming problems, there are two things. One is an artificial variable is in the basis, right, with a positive sign, and we can't have that happening here because we are not dealing with artificial variables at all. The only thing that would happen is we are in both these we are dealing with situations where you are introducing some cuts. In the dual simplex, infeasibility is always indicated by identifying a leaving variable and not identifying an entering variable, opposite of unboundedness. So something like that will happen here. You will want to do a dual cut. You know that there is a variable here with a negative sign, but you are not able to get a corresponding variable to enter. That would mean infeasibility. And we have to think carefully about unboundedness. Unboundedness is the other way. You will be able to do a primal cut, but you enter something, you will not be able to find a leaving variable. That is how unboundedness and infeasibility will be detected in all these problems. Whether it is an IP or whether it is an LP, the cut will take care in case of an IP. In case of an LP, you do not introduce cuts, somewhere during the iteration it will be taken care of. So this is how the entire set of algorithms work. So to quickly summarize what we have learnt in integer programming, we started with reason to treat integer programming as a separate topic. We said that integer programming problems are those where the variables are restricted to be integers. We also saw the classification as all integer algorithms, mixed integer algorithms, or mixed integer problems and 0-1 problems. And then we saw how if you take integer programming as such as a problem and try to solve it by simplex or any LP algorithm, you lose the convexity property of the feasible region. So you will only solve them using tools of linear programming, but then do something in such a way that an LP optimum becomes integer optimum. When an LP optimum becomes integer feasible, it becomes integer optimum, and that is a phenomenon that you observed in all the Gomori cutting plane as well as the all integer primal and all integer dual. You only introduce linear programming kind of constraints that involved continuous variables. At least when you introduce them into the simplex table and proceeded, you always treated them as continuous. The way the thetas were defined and so on, they were treated as continuous. So we were going through a set of linear programming iterations, but then when an LP optimum becomes integer feasible, it becomes integer optimum. So all those things we saw. Then we looked at some formulations. Formulations and advantages of using integer programming as a way to model a set of situations. We saw examples where 0-1 was very powerful. You could model an either or situation, you could model k out of n constraints and so on. And then we also saw how difficult optimization problems are modeled and formulated as integer programming problems, with the examples of the p-median grouping problem, the traveling salesman problem, line balancing problem, the scheduling problem and so on. And then we moved to 0-1 problems, and then we looked at the additive algorithm. It is a very powerful algorithm simply because of the nature of the variables. Variables take only a 0 or a 1, and then we solved a standard problem which was a minimization problem with all constraints of the greater than equal to type and all objective function coefficients non-negative. And then we showed that it was possible to have an efficient algorithm that uses only 3 or 4 vectors in terms of storage and memory. It was a great advantage to work. And then we also saw how any given 0 1 problem can be converted to the standard form, and how nonlinear 0 1 problems can be converted to linear 0 1 problems and solved using the additive algorithm. Then we saw the branch and bound algorithm, which can be used to solve all integer problems as well as mixed integer problems. Branch and bound algorithm essentially at every stage adds 2 constraints to the existing problem. Both constraints are essentially bounds, and we also saw that the constraints being bounds essentially take off areas either as horizontal strips or vertical strips in an existing feasible region, and then solves the remaining problem. And since both the constraints are bounds, one has to do one more iteration or more than one iteration, but one does not have the problem where the constraint size increases. You can straight away do an upper bounded simplex iteration. We have already seen how to do simplex algorithm with bounds. So one could do an upper bounded simplex iteration and keep continuing. The problem size does not increase at every node, even though the number of nodes can go up. We also briefly saw some issues on branching strategy, bounding strategy, and node selection strategy along with this, and we also said that this is a very efficient one because it can handle mixed integer programming in the same way as it handles all integer problems, plus the problem size does not increase at every iteration. Then we looked at cutting plane algorithms. We saw the Gomori's cutting plane algorithm. And in the Gomori cutting plane algorithm, we solve the problem as a linear programming problem. And then if the LP optimum is infeasible to the IP, that is if there are still variables which do not have integer values, we identify one of the variables or the variable that has, in general, the variable that has the largest fractional component, and then generate a Gomori cut. A Gomori cut is different from a branch and bound cut. The Gomori cut is usually not a cut which is in the form of a bound. A Gomori cut is a typical cut which can involve more than one variable, whereas the branch and bound cut always involves only one variable. So the Gomori cut would progressively remove areas from the feasible region and keep on chopping off areas from the feasible region till the corresponding LP optimum is IP feasible, and therefore we get to the optimum. The only drawback of the Gomori algorithm is, as the number of iterations increases, the size or the problem size at every iteration increases by 1. And after looking at the cutting plane algorithm, we looked at all integer algorithms, all integer primal and all integer dual algorithms. The all integer primal algorithm is meant to solve a maximization problem with less than or equal to constraints, and all integer dual algorithm is meant to solve a minimization problem with all greater than or equal to constraints. It was relatively easy to do the primal algorithm and generate a primal cut. The dual algorithm and the dual cut involved a few more computations. Both the all integer primal as well as all integer dual algorithms have the problems of getting into degeneracy, and the example that we illustrated the primal algorithm with ran into degeneracy right through the iteration and also at the optimum. Similarly, the problem with which we demonstrated the dual algorithm also ran into degeneracy at the optimum. So while these are efficient, particularly for hand computation, and particularly when we used this kind of representation of the simplex table, where the cut comes as every time a cut is made, cut comes in the last or an additional row, the computations are easier. In some sense, other than the advantage of hand computation, it is very difficult to say that these could be better than a Gomori cutting plane algorithm or a branch and bound algorithm. When we do hand computation to solve integer programming problems, the all integer algorithms are useful. When it comes to writing computer programs, perhaps the Gomori's method or the branch and bound method would be better compared to all integer algorithms. So, with this we wind up the module on integer programming, and then the next module that we look at are the network problems.